So our next speaker is Andrei from Rutgers University, and she will talk about electric properties of vacancies in graphene.
Okay, a little bit of a change in title. Good afternoon. It's a real pleasure to be here. Good morning, actually. It's not on. Okay, we all know about the wonderful properties of perfect graphene. So it's time to move and to look at what happens when it's imperfect. And what I mean is pluck out one carbon atom and see what happens. And there are three interesting things that happen. One, it develops a local magnetic moment, which is about between 1 and 1.5 Bohr magnetons. Two, there is a condo screening, which can be tuned on and off with a gate voltage. And three, one can charge the vacancy the vacancy is charged, and one can actually deposit charge, and this charge is stable and tunable. So I'm going to talk to you about the third possibility, charging of vacancy in graphene. And I'll show you that we can charge it to large values until we get something that is called atomic collapse. So we all know about the celebrated properties of graphene. The band structure is conical. The excitations are described by ultra-relativistic massless Dirac fermions. The conical band structure leads to a linear density of states which vanishes at the Dirac point. At charge neutrality, the Fermi energy sits right at the Dirac point. Here we have the conduction band and the valence band, which touch at the Dirac point. And in an experiment, you can put your graphene on a 300 nanometer, for example, silicon dioxide, and you can gate it smoothly from electron sector to Fermi sector, to electron to hole sector. Now, when you apply a magnetic field, the band structure breaks up into Landau levels, which, because of the conical dispersion, go like square root of the Landau level index and square root of the magnetic field. There is a zero energy Landau level, which I agree with Efrat is very interesting. There's lots of interesting physics that happens there. And these are flat bands, which are highly degenerate. One interesting consequence of the fact that these are massless Dirac fermions and they're chiral is the so-called Klein tunneling. So you see here, if you have an electron in the red branch here that moves to the right, it cannot scatter back if it hits a barrier. So as a result, it creates its own, it becomes a hole, and it just goes smoothly through as a hole. And when it comes out again as an electron, and that is known as Klein tunneling. One important consequence is that we cannot make quantum dots in graphene. There's no switching with electrostatic potentials, and you cannot guide electrons in graphene with electrostatic potential. Now, it turns out that under certain circumstances, if you have a large charge at the vacancy or some other way of creating a charge, you can confine the electrons. And this is the topic of this talk here. But before I get there, I need the background for atomic collapse. Here is the roughly energy. If you talk about a massive electron in the 1/r potential, or the Bohr atom, and you look at the kinetic and potential energy, the 0-point energy gives you a repulsive force at low distance. The Coulomb potential gives you an attractive force, and as a result, you have a bound state at the Bohr radius, and we get this famous Rydberg, which this is a very nice and insightful way of writing the Rydberg. It's 1/2 mc squared times beta squared, where beta is the Coulomb coupling constant, and this is equal to the positive charge times the fine structure constant. Is there another pointer here? So this is a very small number. Now, as beta increases, Okay, as beta increases, what happens, the binding energy keeps increasing, and you see, of course, the radius becomes smaller and smaller, but eventually you hit the Dirac continuum. So you see that you can no longer use this simple non-relativistic Schrödinger equation. What you need to do, you must include relativistic effects. And when you do that, the equations changes slightly. This is the relativistic expression, and it's quite straightforward to show that if you, and I'm doing it, I'm ignoring angular momentum. If you have angular momentum, the formula is a little bit more complicated, but you get this expression that Dirac showed in 1928, and you see that when beta equals to 1, or the charge of the nucleus is 137, all hell breaks loose, and you don't have solutions anymore. In fact, if you take into account the finite size of the nucleus, you have a small distance cutoff, and in fact there are solutions, but you get a collapse, and you have solution up until 170 atomic number, and beyond that you get the so-called atomic collapse, where the electrons plunges into the nucleus, emitting with a spontaneous emission of electron-positron particles. And this is roughly the phase diagram. Here's the energy as a function of beta, and this is mc squared minus mc squared. Atoms, as we know them, live here. In fact, the periodic table ends somewhere at 118. And if you can get up to this point here, to 170, what happened? You get spontaneous positron production. Now what happens, now what's the connection to graphene? Now we're going to just take the mass of this relativistic particle to 0, and the formula becomes something like this. And you see immediately it's a scale-free problem. There is no characteristic length scale, so there's no minimum here. You have to go to infinity. And you see immediately that there is a phase transition that happens when beta is equal to a 1/2. For graphene, the point is that alpha, the fine structure, and this is the main point here, the fine structure in graphene is a huge number. It's 2. And the reason is the Fermi velocity in graphene, which replaces the speed of light in ultra-relativistic particles, it's 300 times larger than the speed of light. And as a result, the fine structure, effective fine structure of graphene, and that is for interaction within the plane. There's no Lorentz invariance here, is 2. And so what enters here is the QED fine structure constant, the ratio between speed of light and the Fermi velocity. It's a large number. So you get a phase transition at 1/2, which is the equivalent of atomic collapse, but instead of having to go to 170, it's enough to go to about a charge of 1. So when beta is smaller than 1/2, we get this energy is positive. So essentially we get the Klein tunneling. The electron just goes through. There's no confinement. And when beta is is larger than 1/2, you get a attractive potential, and you get the equivalent of atomic collapse. And what you get here is a series of quasi-bound state, which is like a Rydberg series, but not quite. The series goes, it's a geometric series in energy in n instead of a 1/n squared series. There's another important thing that happens here. Let's say that if the Fermi energy is somewhere here, you see that when the kinetic energy vanishes, you go from electron excitation to hole excitations. And there is a classical forbidden region between these R1 and R2 radii. And so you can have tunneling from electrons to holes. And as a result, these are not bound state as in the Rydberg atom, but they are quasi-bound state. So here you have a hole sector. So these are essentially resonances. I just recently became aware of the fact that this is the same problem as Efimov, the Efimov bound state, which is basically whenever you have a problem without a length scale, a scale-free problem, you get this kind of physics. And you can get it for Schrödinger equation where the potential goes like 1/r². And this has been observed in cold atoms when you take 3 atoms. Okay, so the density, now this is density of state as a function of beta in the presence of charge. So when the charge is 0, you get the usual dispersion, Dirac dispersion. And as beta increases, there is a critical value where you suddenly see these states sinking into the Dirac continuum in a sense, and these are the equivalent of the 1s, 2s states in a Rydberg atom. So these are the collapse states. Now comparing the collapse states in real atom, essentially we have no mass gap. So you're going directly from this continuum above mc squared to the Dirac continuum here, to the collapse states. In 2013, a group at Berkeley reported having observed the collapse state. What they did, they took calcium dimers, and when they piled up these dimers, 5 of them, they saw a peak appearing here, and this was somewhere in this phase diagram, somewhere up here, the beginning of the 1s collapse. So so now I'm going to talk about the vacancy. Turns out when you have a vacancy, it's easy to have a much larger charge and to see higher energy levels than the 1s state. So when you pluck out a carbon atom from graphene, of course you break the AB symmetry, but you have 3 sigma bonds dangling left. 2 of them combine, hybridize, and in the end you're left with a 5-9 reconstructed vacancy like this, which has a magnetic moment, as I said, but it also carries a charge of 1. And this is a numerical calculation. So now, in perfect graphene, our experiment, we do ST, scanning tunneling microscopy and spectroscopy. So for perfect graphene, and this is by far the best data that we have, topography gives you this honeycomb structure, density of state, DIDV spectra give you density of state, vanishes at the Dirac point, turn on magnetic field, you see the Landau levels. Now, what happens when we create vacancies? The way we do it, this is, we look at the topography of pristine graphene, and now we bombard it with low-energy helium ions, about 100 eV. And what happens, we kick out carbon atoms, and most of them for these conditions are single carbon vacancies, and they look like this. And when you zoom in, there's this triangular structure, which is exactly what you expect from this reconstructed vacancy. So by finding these structures, we know that we have a single atom vacancies, and then we look at the density of states, and we see that right on the vacancy, we have a strong peak, which very rapidly decays as you move out, as you move away. It decays within about 2 nanometers. So there's a vacancy peak, which is tightly localized, and it's pinned to the Dirac point. So whenever you gate the sample, the vacancy peak just marks the Dirac point. Now, here, in order to determine the charge of this vacancy, we do Landau level spectroscopy. So this is the Landau level sequence as a function of distance from the vacancy, and this is right at the vacancy. You see these very strong peaks. These peaks tell us exactly what the charge is of the vacancy, and this is a simulation, and you take the distance between these peaks, and it's roughly about the distance about 0.1. It is about whatever it is, 50 millivolts, and you get a beta of 0.1. So by looking at these peaked Landau levels, we can tell what the charge is. And this charge is much smaller than predicted theoretically for an equilibrium state. So now what we do, we pulse the vacancy with voltage pulses right at the position of the center. We apply about 2 volts. And we see that the charge grows, and the Landau level starts bending, and this is a direct consequence of the charging. And from the bending, we can calculate the charge, and the 2 peaks, it's about 0.6 here. Beta is about 0.6. So the vacancy charge gradually builds up with pulsing, and the charge is stable. It stays there until we warm up the experiment. And here's a few vacancies, and the evolution of beta is a function of charging. Notice that it never goes back, it always goes up, and it kind of saturates. Probably not, we can actually go higher. So this is how it works. So now, how am I doing time-wise? I'm doing fine. Okay. So here are the, so this is a simulation, this is the experiment, and these are the vacancy peaks. And you see as we pulse, the beta keeps increasing. So we have, this is before pulsing, and it keeps going up, down, and eventually it sinks below the experimental horizon. And then we continue to pulse it. And something very interesting happens there. There's a new sequence of peaks that marches in from the right here below the Dirac point. And now we can also compare them to the atomic collapse peaks. So here, and you see that we are marching up in beta here. So we've gone down the 1s branch here. There's another peak that evolves here. This is the 1s prime, which is a satellite. And that has to do with the fact that we're breaking the sublattice symmetry. But most importantly, we have a new peak here coming, and that is equivalent to 2s. So that now we have two states here. We have a 2s, 1s. You can take the ratio, and it actually fits the FIM of physics. We just realized this a couple of days ago. Now, there's two sequences of peaks. How can you tell what is what? And the way to tell is from the density of state maps. The vacancy peaks are very tightly localized. They're within 2 nanometers. When we see the collapse peaks, they're huge. Okay, they're about an order of magnitude bigger than the vacancy peak. So now we can look at the spatial dependence in more detail. And this is the data, and this is the simulation. The yellow line here is the line of the where the Dirac point sits. The Dirac point always rides on the potential, on the external potential. So it rides on the 1/r potential. So everything that's underneath the Dirac point is Hall sector. These are electron sector. And now we're going to do maps at these various energy. The 1s is here. Higher up is the 1s prime, the satellite. And then we have the 2s. And we're going to map. We're going to do density of state maps of these states. And now you see the 1s state, which is this state, has a tight core here of about 15 nanometer, and then there's a halo of holes. So we have an electronic state here, and these are hole states. So this is the equivalent of the positron production in atomic collapse. And the 1s prime state is larger, and the 2s state is here. And finally, actually, I'm doing pretty well time-wise. Okay, so this is, so we have a supercritical charge here. And this is a mechanism to essentially to beat Klein tunneling, to confine electrons with an electrostatic potentially. Normally, you cannot do that in graphene. If you want to confine electrons in graphene, you either have to cut your sample or apply a magnetic field, which is another whole story. And finally, I'm going to show you what happens with gating. I mean, you might wonder what screening does to this charge. How come the electrons, the itinerant electrons in the conduction band don't screen this charge? And so this is a gate dependence. So we're going from hole doped to electron dope. The red arrows here are where the Dirac point is. So at this point here, this is the Dirac point is here, and we have our collapse resonance, which is below it. Zero in STM, 0 is always the Fermi energy. So you see that as we gate it into the electron sector, of course the Dirac point marches down here, but you see that the Fermi energy eventually will cross the collapse resonance. So, and these are the betas as a function of gating. So you get a pretty large beta when you're strongly in the whole sector. So this is P doped, this is N doped, this is where the Dirac point is, and this red square here is where the Fermi energy coincides with the collapse resonance. So on this side, on the left side of the red square, the Fermi energy is below the resonance. And wait, am I sorry. Yes, so on the left side here, the Fermi energy is below the resonance, and the right side here, it's above it's marching above the resonance here. So what is extremely surprising to us is the screening is so asymmetric. So when we're on the p-doped side, the screening is strong. So we actually can get up to, we can tune beta from 0.9 to 1. But as soon as we cross onto the n-doped side, there's no more. The peak disappears. I don't know if this is surprising. There are all sorts of ideas about what's going on. One possibility is some sort of a correlated state. Another possibility is we start out with a strong electron-hole asymmetry because of the charge there. But I think the reason for this strong asymmetry is not yet understood. One other point to make is the reason we do see this charge is because the Fermi vector, wave vector, the Fermi wavelength is much, much longer than the size of the collapse state. So at the doping, in the range of doping here, the Fermi wave vector is about tens of nanometers or many tens, about 100 nanometers, whereas the size of this this artificial atom is about 10 to 20 nanometers. So it just cannot screen it. So the screening length is much, much longer than the size of the charge. Oops. OK, and this brings me to the summary. So basically, the message is that vacancies in graphene can stably host a positive charge. The charge can be pushed into the supercritical regime. We see a sequence of bound states that form an artificial atom, and that screening is strongly electron-hole asymmetric. And these are the people who did the work in my group, and here are our theoretical collaborators who did that tight binding simulation. Thank you for your attention.
Question?
I'm a little confused about this electron-hole asymmetry. I mean, you say that the impurity is always positively screened, right? So
Impurity is always positive, yes.
why do you expect electron-hole
But if you look in any kind of solid state book, if you put an impurity that, regardless of the charge, the screening, it will be screened either by positive or by negative charges, right? The screening is just determined by the screening length. You don't care about the charge, right? So in one case, you attract the electron. In the other case, you push them away. But the screening should be symmetric if the band structure is symmetric, which we don't see here.
Is this suspended graphene or is this silicon substrate?
OK, so this is a double layer of graphene. It's not a bilayer. It's a double layer. So we put another layer at a large angle of rotation so you don't get coupling between the two layers. And the reason we do that is to decrease the amount of random fluctuations from the silicon dioxide substrate. It works on boron nitride as well. We wanted this. So the screening is very nonlinear in graphene. So two layers do much more of graphene, do much more screening than having doubling the carrier density. So it's a very efficient way to have a clean sample, essentially.
I would value any comments you care to make about the magnetic properties. And the background is that in our laboratory we generate various kinds of carbon nanoparticles by running an electrical discharge in ethanol. And it turns out that some of these particles are strongly magnetic.
So as you know, graphite and graphene is one of the most diamagnetic materials that we know of, right? There shouldn't be a magnetic moment, except, I'm not talking about magnetic impurities, except when you break the sublattice symmetry. Right? There's a famous Lib theorem that tells you that if you break the sublattice symmetry, you're going to have a net magnetic moment, which is equal to the unbalance between the two sublattices. So if you have a zigzag edge, it's magnetic. If you have a single vacancy, it's magnetic. So these vacancies have a magnetic moment, one Bohr magnetode that comes from the dangling bond that's left behind, and about a half Bohr magnetode, between a half and 0.1, depending on the density of the single atom vacancies, which comes from the missing electron in the pi band. The other two are hybridized. So there is a magnetic moment, has been observed, it has been observed directly in a way that I'm not particularly happy about, because with squid magnetometry, and for that you need a huge sample. So what you take graphite, you exfoliate it, you blow it up, and then you irradiate it. They irradiate, this is a Manchester group, irradiated it with protons. And they see huge, it's magnetic. And they don't see contrast screening, in contrast to what we see and in contrast to what transport people see. But if you see a magnetic moment, I'm not at all surprised. The only way not to see a magnetic moment, to have a perfect sample. I can't hear you. What dye vacancy doesn't work. No, actually, no. Well, I think the simple answer, we didn't try. And I shouldn't say it doesn't work. The answer is I don't know. You know, we start with a single vacancy because it's the simple defect we can make. Now, the conditions for dye vacancies are a little different. So the energy of your helium ions has to be a little higher for dye vacancies. So we just don't have them there, or at least they're very hard to find. So the simple answer is we haven't done it. And actually, it might be quite interesting to go there. Once we understand what happens with single atom vacancies, it would be time to move to dye vacancies, yes.
So, next speaker here.